Question 1, we've got the Venn diagram showing the three events A, B, and C, and we're asked to find the probability of B dash. Well, B dash means outside of B, so we want the 0.15, the 0.13, and the 0.12, which means that the probability of B dash is simply going to be the sum of these three probabilities, 0.15 plus 0.13 plus 0.12, which gives an answer of 0.4. Now for the probability of A union C means all of A or C, so I simply need to consider these regions here. So it's the 0.15, the 0.20, the 0.23, and the 0.12. So if we add this up, it's the probability of A union C. 0.15 plus 0.20 plus 0.23 plus 0.12, and this gives an answer of 0.7. And then we have to find the probability of A given B dash, this conditional probability. So we know for sure that we are outside of B. So outside of B means I'm here, here, or here. And the question is, what's the probability you are in A? So what I have double ticked, the 0.15, over what I have ticked once, so this, and this. So we have that the probability of A given B dash is simply 0.15 over 0.15 plus 0.13 plus 0.12, which gives an answer of 3 over 8. In question 2, we've got a stem and leaf diagram showing the ages in years of the residents in a care home, and we need to find the median age of the residents. Well, we need to start by determining how many observations we've got, so I will add up the numbers shown here, which is the number of observations in each row of the stem and leaf diagram to give me the total number of observations. So I'll be doing 1 plus 1 plus 9 plus 11 plus 7 plus 2, which gives an answer of 31. So to find the median, the middle value, I'll be doing n over 2, which is 31 over 2, which is 15.5. I need to round this up, and therefore the median will be given by the 16th observation. So going to my stem and leaf diagram, the first 11 observations were up to here. So the 12th, 13th, 14th, 15th, 16th observation is the 74, and that's the median. In B, we need to find the interquartile range, so I will start by finding the lower and the upper quartile. For the lower quartile, I'll be evaluating n over 4, so that's going to be 31 over 4, which gives an answer of 7.75. Again, this is not an integer, which means that the lower quartile will be given by the 8th observation, so I always round up. So we've got 1, 2, 3, 4, 5, 6, 7. The 8th observation is a 68, and using a similar approach for Q3, I will evaluate 3n over 4. So I'll be doing 3 times 31 over 4, which gives an answer of 23.25. So I will round up once more to say that Q3 will be given by the 24th observation. So we've got 1, 2, and 9, it's 11, and another 11 is 22, 23, 24. So my upper quartile Q3 is 80, which means that to find the interquartile range, I will simply be doing Q3 minus Q1, which is 80 minus 68, which gives an answer of 12. We then proceed in being given a rule for defining outliers here. So any value that's either more than 1.5 times the interquartile range below the lower quartile, or more than 1.5 times the interquartile range above the upper quartile is deemed to be an outlier. So I need to start by finding the limits for outliers. So I'll do Q1 minus 1.5 times the interquartile range, which is 68 minus 1.5 times 12, which gives an answer of 50, and Q3 plus 1.5 times the interquartile range, which is 80, plus 1.5 times 12, which gives an answer of 98. These are the limits beyond which outliers are to be found. So if I look at my stem and leaf diagram, we notice that the only value which is beyond this limit is the 43. So I say 43 is less than 50, and hence we conclude that 43 is the only outlier. So we had to show all calculations here in order to arrive at any outliers within the data. We are then asked to draw a box plot to summarize this data, and there are actually two box plots that could be drawn, both of them scoring the 3 marks. We're going to discuss both of them here. I will start by drawing a cross at the position of the outlier at 43, and then we draw the box. So the box is here. It's the lower quartile at 68, the median at 74, and the upper quartile at 80, and we then draw the whiskers. So on the right hand side we go up to 97, which was indeed the maximum age observed, and on the left hand side I'll go up to 50. 50 was the theoretical limit we calculated in part C. This was the limit calculated here. So I'm using the left whisker here up to the theoretical limit. Alternatively, another box plot we could have drawn is again having an x at 43. We do have the box again at exactly the same place. And on the right hand side, we still go up to 97 because we know that we have not seen anything beyond 97. But on the left whisker here, we go up to the last value that was not an outlier. If we revisit our stem and leaf diagram here, we see that 43 was an outlier and the value immediately after it was 54. So the left whisker will go up to 54, which was the last value not to be an outlier. In question 3, we've got the weights of packages arriving at the factory being normally distributed with a mean of 18 kilograms and a standard deviation of 5.4 kilograms. So we need to find the probability that the package weighs less than 10 kilograms. I will start by defining that my random variable x is the weight and follows a normal distribution with mean mu 18 and variance sigma squared being 5.4 squared. We're trying to find the probability of x being less than 10, so I will standardize by deducting the mean and dividing by the standard deviation. So it's the probability of z being less than 10 minus 18 over 5.4, which gives the probability of z being less than minus 1.48. Now for me to use the normal probabilities table, I need to have this z value here being positive, so I will write this as 1 minus the probability of z less than 1.48 and look up the value on the table provided in the formula booklet. So we see that 1.48, the corresponding probability is 0.9306, and therefore we've got this is 1 minus 0.9306, which gives an answer of 0.0694. Please note that if you are using a calculator, then you are getting an answer of 0.069239, and the examiner here is accepting anything between 0.0692 and 0.0694. In B, we have that the heaviest 15% of packages are moved around the factory by Jemima using a forklift truck, and we need to find the weight in kilograms of the lightest of these packages. So essentially we're being asked to solve probability of capital X being greater than small x is 0.15. In other words, we need to find the value of small x here so that anything above this weight will have a probability of 0.15, and therefore it will constitute the heaviest 15% of the packages. So to do this, I will standardize. So it's the probability of z greater than x minus 18 over 5.4 being equal to 0.15. And for me to extract the corresponding z value, I will be using the small table of values from the normal distribution. So the table is giving the probability of exceeding a specific value. I go for 0.15 and I read off 1.0364, which means that x minus 18 over 5.4 is equal to 1.0364. We will cross multiply to get x minus 18 is 1.0364 times 5.4. So we have that x minus 18 is 5.59656, which leads to x being 23.6 kilograms. The examiner is accepting anything which rounds to 23.6 kilograms. In part C, we've got that one of the packages not moved by Jemima is selected at random, and we need to find the probability that this specific package weighs more than 18 kilograms. Well, it makes sense to draw a bell-shaped curve to see exactly what's happening here. So this is the distribution of the weights. Its mean is at 18. We know for sure that this package was not moved by Jemima, so it means that it's somewhere here. It's certainly less than 23.6 kilograms in weight that we found from before. So we know the probability of exceeding this is 0.15 because 15% of the heaviest were moved by Jemima, which means that the probability of being on the left side here is 0.85, and we're wondering what's the probability that this weighs more than 18 kilograms. In other words, what's the probability that I'm in this region of my bell-shaped curve? So we're being asked to find the probability of x being greater than 18, given that x is less than 23.6. This is conditional probability. So from the bell-shaped curve, we see that it's the probability that we are between 18 and 23.6 divided by the probability of x being less than 23.6. So if all of this here is the 50%, the 0.5, it means that this region here is simply 0.35. So the probability I'm between 18 and 23.6 is 0.35 to be divided by the 0.85, and this gives an answer of 7/17. In part D, we've got the delivery of 4 packages. The weights of the packages are independent, and we need to determine the probability that exactly 2 of them will be moved by Jemima. Well, we know that the probability of a package being moved by Jemima is 0.15. Remember, we've got 4 packages here, so we are wondering what's the probability that exactly 2 of them will be moved by Jemima. We will start by listing all possibilities. It could be the first 2 moved by Jemima and the other 2 not, or maybe the first, not the second, the third, and not the fourth. So maybe the first, not the second, not the third, but the fourth, or maybe not the first, the second, the third, but not the fourth, or not the first, the second, not the third, the fourth, or maybe the first 2 were not moved by Jemima, but the last 2 were. There are 6 possible scenarios here, and each of them has the same chance of happening because we've got the first 2, for example, being moved by Jemima, so 0.15 times 0.15, and the last 2 not, so 0.85 times 0.85. And this will be multiplied by 6 because this is the number of different combinations that might lead to 2 of the 4 being moved by Jemima. So if you put this on the calculator, this is 0.0975. For those of us who are familiar with the choose notation, we can see that this is 4 choose 2 because out of the 4 packages, we choose 2 of them to be moved by Jemima and 2 of them not to be, and this is giving 6. It's the number of different combinations, so the 6 that we got here. In question 4, we've got a spinner that can land on the numbers 10, 12, 14, and 16, and we're told that the probability on landing on each number is the same, and we've got the random variable capital X representing the number that the spinner lands on, and we need to state the name of the probability distribution of X. Well, since all outcomes are equally likely, then we're looking at a discrete uniform distribution, the keyword here being the uniform. We then need to write down the value of the expectation of x and then find the variance of x. I will actually start by drawing up a table, the probability distribution of x. We know that x can take values 10, 12, 14, and 16 with equal probabilities. So that means that all the probabilities are a quarter. So we can simply state that by symmetry, the expectation of x will be the middle value here. So we simply have that the expectation of x should be 13. Alternatively, you could have done the formula for the expectation where you multiply x by the probability and you add them up. You will get 13 again. Now to find the variance of x, I will start by finding the expectation of x squared. So we do x squared times the corresponding probability. So 10 squared times a quarter plus 12 squared times a quarter plus 14 squared times a quarter plus 16 squared times a quarter, and this gives an answer of 174. Well, we know that the variance of x is given by the expectation of x squared minus the square of the expectation. So this is 174 minus 13 squared, which gives an answer of 5. We then have a second spinner that can land on the numbers 1, 2, 3, 4, and 5 only. The random variable y represents the number that this spinner lands on, and this is the probability distribution of y. We need to find the expectation and the variance of y, so we will do exactly the same, pretty much that we did in the previous part. So we've got that the expectation of y will be found by multiplying the y's by their corresponding probabilities. So it's going to be 1 times 4 over 30 plus 2 times 9 over 30 plus 3 times 6 over 30 plus 4 times 5 over 30 plus 5 times 6 over 30, and this gives an answer of 3. This is the expectation of y, and for the variance of y, I will start by finding the expectation of y squared. So that's going to be 1 squared times 4 over 30 plus 2 squared times 9 over 30 plus 3 squared times 6 over 30 plus 4 squared times 5 over 30 plus 5 squared times 6 over 30, and this is giving me an answer of 54 over 5, and therefore the variance of y will be the expectation of y squared, so 54 over 5, minus the square of the expectation, so 3 squared, so this is 9 over 5. We then have that the random variable w is ax plus b, with a and b being constants and a being positive. We have that the expectation of w is equal to the expectation of y, and the variance of w is equal to the variance of y, and we need to determine the value of a and the value of b. So starting with the fact that the expectation of w is equal to the expectation of y, we know that w is ax plus b, so the expectation of ax plus b is equal to the expectation of y, which we found to be 3. So this means that a times the expectation of x plus b is equal to 3. And we know that the expectation of x is 13, so 13a plus b is equal to 3. We've got one equation linking a with b. Moving on to the fact that the variance of w is equal to the variance of y, we have that the variance of ax plus b is equal to the variance of y, which is 9 over 5. We know that when we've got the variance of ax plus b, the b is not affecting the variance, but the a comes out in squared form. So a squared var x is 9 over 5. The variance of x was 5, so we have 5a squared is 9 over 5, which leads to a squared being 9 over 25, and therefore we say that a is plus minus the square root of 9 over 25, so a is plus minus 3 over 5, but since a is given to be positive in the question, it was stated originally here, we conclude that a must be 3 over 5, and based on this we can come back here to find the value of b. So I'm substituting A with 3 over 5. So 13 times 3 over 5 plus B is equal to 3, which leads to B being 3 minus 13 times 3 over 5. And we get that B is equal to minus 24 over 5. We then have that each of the spinners is spun once, and we need to find the probability of W being equal to Y. So remember that we had X attaining values of 10, 12, 14, or 16. We have that W is defined to be 3 over 5x minus 24 over 5, now that we've got the values of A and B. So for each value of x, I will calculate the corresponding value of W. So when x is 10, we get that W is 6 over 5. When x is 12, we get that W is 12 over 5. And when x is 14, we get 18 over 5. And when x is 16, we get 24 over 5. So these are the values that the random variable W can attain. On the other hand, Y can attain the values of 1, 2, 3, 4, or 5. And we're looking for the probability of W being equal to Y. Well, we see that in no case do we have a value for W that could be equal to the value of Y, because all of these are non-integers and all of these are integers. So the probability of W being equal to Y is simply 0. In question 5, we've got a company director wishing to introduce a performance-related pay structure for her managers. She took a random sample of 15 managers. We've got their annual salaries Y in thousands of pounds, and she calculated a performance score X for each of these managers. We've got the results illustrated on a scatter diagram, and we need to describe the correlation between performance score and annual salary. Looking at the scatter plot, we see that the points are lying close to a straight line with a positive gradient. It means that as performance score increases, annual salary also increases, which means that we can say that this is simply positive correlation, or we could also say that as performance score increases, annual salary increases as well. We are then told that the results are summarized in the following statistics, and we need to show that SXY is 2006 and also find SYY. Well, we know that the definition for SXY is simply the sigma XY minus the sigma X sigma Y over N. So we will be substituting sigma XY with 19,428 minus the 465 times the 562 over the N, which is 15, and this is giving an answer of 2006 as required. This is SXY. Now for SYY, we've got the definition of SYY being the sigma Y squared minus the sigma Y all squared divided by N. So in this case, it's going to be 23,140 minus 562 squared over 15, which gives an answer of 2083.73. Anything which rounds to 2080, so to 3SF, will be acceptable by the examiner. In part C, we need to find the product moment correlation coefficient between performance score and annual salary. Well, we know that the PMCC R is given by SXY over the square root of SXX SYY. We have found SXY to be 2006 over the square root of 2,492 times 2083.73. This gives an answer to 3 significant figures of 0.880. It's positive correlation, which confirms what we have seen on the scatter plot earlier. We are then told that the director believes that there's a linear relationship between performance score and annual salary, and we need to state, giving a reason, whether or not this data is consistent with the director's belief. Well, there are two things we could say to conclude that the director's belief is consistent with the data. One thing to say is that since R is close to 1, then the data is indeed consistent with the director's belief. R being close to 1 indicates a strong linear association, so that's what the director is believing. Alternatively, we could say that since points lie close to a straight line, again, data is consistent with a linear model, so the director's belief is supported. In part E, we need to calculate the equation of the regression line of y on x in the form y is a plus bx. We need to give the value of a and the value of b to 3 significant figures. So we will start by calculating b. We know that b is sxy over sxx, and we've got these quantities. It's 2006 over 2492, which is giving us 0.804975 ... And to find a, I will be doing y bar minus bx bar. So it's the mean of y, 562 over 15, minus the 0.804975 ... times the 465 over 15. This is giving me an answer of 12.51241. So we conclude that the model is of the form y is 12.5 plus 0.805x. In F, we need to give an interpretation of the value of b. Well, b is the gradient here. It's the 0.805, which is representing the change in y for every extra unit in x. We need to put this in context. So we need to say that for every unit increase in performance score, the annual salary will increase by 0.805 thousand pounds. We need to mention the thousand here, or alternatively say 805 pounds. In G, we need to plot the regression line on the scatter diagram. To do that, I will have to generate 2 points on the line. Of course, it's easy to generate the y-intercept, so I would simply say that when x is 0, we see that y is 12.5, and I will also put x is 50, so a point towards the right side of the spectrum. So when x is 50, we get that y is 12.5 plus 0.805 times 50. This is giving an answer of 52.75. So I've got 2 points that lie on the line of best fit. I'm going to use these 2 points to draw the line of best fit. So I'm starting by plotting the 2 points. I'm plotting the 0, 12.5. I'm plotting the value we found for x is 50 over here, and we're joining together the 2 points. This is the line of best fit. Now remember that your line of best fit should be passing always through the point with coordinates x bar, comma y bar. So remember that x bar is 465 over 15, which is 31. Y bar is 562 over 15, which is 37.5. And therefore, the point 31, 37.5 is indeed a point on the line. It's the point x bar, comma y bar. Now, the examiner will give you full marks for this part if your line extends at least between 10 and 50. So you should cover the range of values observed here. So it's a good idea to always extend it over the full range you see here. We are then told that the director hears that one of the managers seems to be underperforming, and we need to circle the point that best identifies this manager. So looking at the scatter plot, we are looking for someone who is underperforming, someone who is getting a lot of money, but he's not having a high performance score. So it must be this guy here who is getting a salary of in the range of 48,000 per year, but his score is only about 25. So you can see that he's well above the line of best fit. So his salary should have been here for this performance score. However, it's a lot more. So he's underperforming if we take into account his performance score. And finally, in I, we have to estimate to 3SF the new salary of a manager with a performance score of 30. So we will simply say that when X is 30 and substitute this value into the line of best fit we obtained earlier, Y is 12.5 plus 0.805 times 30. This gives an answer of 36.65. Remember, this is thousands of pounds, so my final answer should be 36,650. If you stop at 36.65, you will be penalized with a mark. They are asking for the new salary, so have to give it in the right form with the right units. It's thousands of pounds. In question 6, we are told that a disc of radius a centimeter is rolled onto a horizontal grid of rectangles so that the disc is equally likely to land anywhere on the grid. Now each rectangle is 5 centimeters long and 3 centimeters wide, with no gaps between rectangles, and the grid is sufficiently large so that no disc rolls off the grid. And if the disc lands inside the rectangle without covering any part of the edges, then a prize is won. And we need to consider the possible positions for the center of the disc to show that the probability of winning a prize is a fifth. So we really need to draw something here to get a visual understanding of what's happening. So I will start by drawing my rectangle, which measures 5 by 3 centimeters. So we've got discs of radius a centimeter, and I will draw such a disc, and I will consider the different positions where it could be. One position would be exactly so that it touches upon the upper edge here and the left edge here. So if it's a centimeter within the vertex here, so a centimeter to the right and a centimeter down, and it's just not touching the edges. And there are actually 4 critical positions for a disc. So one of them is shown here, then we've got another one at the right top corner, and then at the bottom right and at the bottom left corner. So we really need the disc to land inside this rectangle here, which is created, in order to ensure that we are not covering any part of the edges of the rectangle, and therefore a prize is won. So essentially, we are looking at what I have shaded here. It's a rectangle that measures 3 centimeters by a centimeter, because if I have the original height to be 3 centimeters, and I need to be a centimeter within, then I lose 2 centimeters and I'm left with a centimeter here. And similarly, if the length was 5 and I want to keep within a centimeter within the edges, then I'm left with a length of the inner rectangle of 3 centimeters, and therefore we can calculate the probability of winning a prize simply being this area divided by the total area. So the probability of winning a prize is 3 times 1, the area of the inner rectangle, over 5 times 3, which is the area of the original rectangle, which gives an answer of a fifth as required. We then have that the group of 15 students each roll the disc onto the grid 20 times, recording the number of times X that each one of them won a prize. And we've got a summary of the results here, the sum of the X values and the sum of the squares. And we need to determine the standard deviation for the number of prizes won per student. Well, we know that the variance sigma squared is given by the average of the squares, so sigma x squared over n, minus the square of the average, which is sigma x over n, all square. So that's going to be 295 over 15 minus 61 over 15 all square. This is giving me the variance. See, this is 704 over 225. We are being asked to find the standard deviation, so this is simply the square root of 704 over 225. We will be giving our answer correct to 3 significant figures, which is 1.77. We then have that the second group of 12 students each roll the disc 20 times, and the mean number of prizes turns out to be 3.5 with a standard deviation of 2. And we need to work out the mean and standard deviation of the number of prizes won per student for the whole group of 27 students. So we can draw up a table. We've got 2 different samples that need to be combined. So we've got the first group, the second group, the overall, and we know that in the first group we had 15 students, whereas in the second group it was 12 of them. Now the sum of the x's for the first group was 61, the sum of the x squares was 295, and we have been given that the X bar, the average for the second group was 3.5, whereas the standard deviation was 2. I'll have to use this information here to derive the sigma x and the sigma x squared for the second group in order to combine them together. So let's start by reminding ourselves that x bar is sigma x over n and sigma squared is sigma x squared over n minus sigma x over n all squared. We have that the mean for the second group was 3.5 and the n was 12, so 3.5 is sigma x over 12. I will cross multiply to get that 42 is the sigma x. And then we have been given that the standard deviation sigma is 2, so 2 squared is sigma x squared over 12 minus x bar, which was 3.5 squared, which means that 2 squared plus 3.5 squared is sigma x squared over 12. This leads to 65 over 4 is sigma x squared over 12, and I can cross multiply with 12 to arrive at 195 being the value of sigma x squared. This means I can go back to my table here. For sigma x, we had 42 for the second group, and for sigma x squared, we had 195. So for the overall, the combination of the two samples, we have 27 students. The sum of the x's is simply 61 plus 42, which gives me 103. And the sum of the x squares is 295 plus 195, which gives an answer of 490. And these are the values I will use to find the overall mean and the overall standard deviation. So for x bar, we do the sum of the x, which is 103, over n, which is 27, which gives an answer of 3.81. And for sigma squared, I'm doing sum of x squared, which is 490 over 27 minus sigma x over n all squared. So this is giving an answer of 2,621 over 729. So the standard deviation will be the square root of this number. So 2,621 over 729 square root, which gives an answer of 1.90. We then have that the 27 students also recorded the number of times that the disk covered the corner of a rectangle and estimated the probability to be 0.2216 to 4 decimal places. And we need to explain how this probability could be used to find an estimate for the value of pi and state the value of this estimate. So again, let us draw the original rectangle measuring 5 by 3. We are now recording the number of times we are covering the corner of a rectangle. So essentially, I will be placing my disk on the corner exactly so that I'm covering the corners. So it could be there, 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 or there, 4 possible positions. And if the center of the disk is anywhere here, then I am bound to be covering the corner. So essentially, we're looking at the shaded regions shown here, and the probability of 0.2216 is equivalent to the proportion of the shaded area compared to the total area. So we see that we've got 4 quadrants, so together they make a full circle which has an area of pi r squared, with r being 1. So pi times 1 squared is the shaded area over the total area, which is 5 times 3. And this is approximately 0.2216 according to the findings of the students. So we have that pi is approximately 0.2216 times 15 if we cross multiply, which gives pi to be 3.324. Well, we know that pi is 3.141 ... This is based on a sample of 27. We don't expect too much exactly the value of pi. It is close enough. It is an estimate of pi based on the given experiment.